this section we'll talk about eigenstuff, meaning eigenvalues and eigenvectors. I've always thought that these have surprisingly intimidating names for what at core, simple concept they are. And hopefully you'll feel the same. So if we're looking at a linear transformation by matrix W, as we've done a bunch already, sometimes we notice something interesting, which is that we have vectors that don't change direction. So here you can see all of these vectors are changing direction, and by that I just mean they're changing the angle that they're pointing at. But G and C are not doing that. They are still pointing in the same direction as before the transformation. And so any vector that doesn't change direction when transformed by the matrix W or multiplied by the matrix W equivalently is an eigenvector of that matrix. So here, G and C are eigenvectors of the matrix W. Eigenvectors don't change direction, but they can change length. So here you can see that G and C are still eigenvectors, but they are changing length after the transformation. C is longer here than it is here. Each eigenvector has a corresponding eigenvalue, and the eigenvalue of a matrix tells you how much the eigenvectors change length. And so it's just a scalar value that tells you how the eigenvector is stretching or getting smaller. And so eigenvalues can be negative, and if eigenvalues are negative, that means that the eigenvector is flipped after the transformation. So I was a little bit inaccurate earlier when I said that eigenvectors don't change direction. They can change to the opposite direction as long as they lie along the same line. So here C and G are still eigenvectors. So to formalize this concept in math, we can write out the equation of a matrix W times its eigenvector equals the eigenvalue times the eigenvector. So this is saying that when the eigenvector is transformed or multiplied by W, it will equal itself times some scalar, which, if you remember from the last tutorial, means that the length can change, but the direction cannot, because that is scalar multiplication. And so any vector that this is true for is an eigenvector of W. So this seems like kind of a random concept maybe, but it turns out that eigenvalues and eigenvectors are hugely helpful in many, many applications. At a very core level, looking at how the eigenvectors change before and after transformation can help us understand what transformation occurred in an even more intuitive way than looking at the basis vectors. And you will dive into that in the next exercise. But here you can see these are eigenvectors of the matrix doing this transformation. And you can see that A isn't changing, and B has just reflected across itself, but is the same length. So you instantly know that this transformation is performing a reflection across the axis defined by A, or I should say the line defined by A. Eigenvalues and eigenvectors are also extremely important for understanding dynamical systems, so you'll get into that a little if you get to the bonus tutorial today, but you'll also see that a lot in the Comp Neuro course. Alright, so now you will use eigenvectors to understand how a matrix is transforming space.